Hello, and welcome to another video on curve sketching. In this video, we're going to use the first derivative test and concavity to sketch the graph of this function here. We have f of x, which equals x to the 1/3 times x plus 4. Now, before we move on to actually doing it, I want to take a look at something online real fast. We have my website. If you click on Calc 1 and you scroll down to Applications of Differentiation, there is a link called Examples of Curve Sketching with step-by-step instructions. If you go ahead and click that, and I believe it's about halfway through, probably on page 11 or 12. There we go, Summary of Curve Sketching. And you would go through all of these steps, and then in the end, I think it's step 7, you finally have sketch. Now we're going to focus mainly on the x and y intercepts, which is step 2, and steps 5 and 6, which is to use the first derivative and the second derivative. So let's go ahead and start now. Okay, so let's find the x and y intercepts. Now to find the x-intercepts, what we're going to do is we're going to set the equation equal to 0, or the function equal to 0. We're going to go ahead and solve. Now fortunately, it is factored for us. So all we're going to do is we're going to set each factor equal to 0. So we got x to the 1/3 equals 0 and x plus 4 equals 0. Should be easy to solve. This should just give me x equals 0, and this should give me x equals -4. So I have the intercepts, the x-intercepts, 0 comma something, and -4 comma, 0. I should say that something is going to be 0 because it's the x-intercept and the y value has to be 0. Okay, so we got our two x-intercepts. Let's take a look at the y-intercept. What we're going to do is plug in x equals 0. Well, if we plug in x equals 0, we're going to get 0 to the 1/3. 0 plus 4. That's just 0 times 4, which is 0. So the y-intercept is also 0, 0. All right. These are the steps to find the local extrema of a function. You're first going to find f prime, and then you're going to follow the rest of these steps, which is to set the derivative equal to 0, figure out when the derivative doesn't exist, draw a number line, and you'll follow the rest. This is a nice table to have with you, because once you do the number line, this is going to tell you when you are a local max or min, or when you're nothing. Alright, so let's find f prime. Now just to remind you, f of x is x to the 1/3 x plus 4. And to warn you, the derivative is going to take a little bit of time, so rewatch it a few times if you have to. It is going to be a product rule, so we have f prime, which is going to be x to the 1/3 times the derivative of the second piece, which is x plus 4, plus, and then you got x plus 4 times the derivative of the first piece. Okay, so we got x to the 1/3, and you're going to multiply by the derivative of x plus 4, which is just 1. Plus, and you're going to get x plus 4 times the derivative of x to the 1/3. Now that's going to be 1/3 x to the -2/3. Alright, now we just have to simplify, because at some point we will have to set this equal to 0, so we do need to factor. What we can do is notice that we have an x to a power and another x to a power. So I can pull out x2, and then it's going to be the smallest power. So between 1/3 and -2/3, we're going to pull out a -2/3. Now that's all they have in common. This has an x plus 4, but this does not. Alright, when I pull an x to the -2/3 out from this, you get x2, and you have to be careful. What would this exponent have to be so that when you multiply this back in, you're going to get 1/3. And it's going to be 1, because when you multiply these two back in, you add the exponents, and you get 1/3. Plus, and the x plus 4 and the 1/3 is still there. Alright, we'll keep going with simplifying. This is going to be x to the -2/3, and this is going to be x plus 1/3 x plus 4/3. And just keep cleaning it up a little bit. We're going to get x to the -2/3, and then this is x plus 1/3 x, which is 4/3 x, plus 4/3. And if you factor out 4/3, because that's what they both have in common, we have this. So this is what I get when it is factored. You can rewrite this as 4 x plus 1 over, and then you have the 3, and then you can bring that negative 2/3 down to the bottom, make it positive. So there is our first derivative. Next, we're going to set the first derivative equal to 0, and then figure out when it does not exist. Now, to remind you, the first derivative was 4x plus 1 over 3x to the 2/3. Okay. Oops. So we have f prime of x equals 0. So that would be when 4x plus 1 over 3x to the 2/3 equals 0. Well, the only time a fraction is going to equal 0 is if the numerator equals 0. So all we're going to do is we're going to set the numerator equal to 0. And when we solve that, we get -1. Now, when you want to know when the first derivative does not exist, well, that's when the denominator equals 0. So what we're going to do is we're going to set 3x to the 2/3 equals 0. And by doing that, you find that x has to equal 0. So we have two critical values. We have 0 and -1. So what we're going to do is draw a number line and plot the critical values. So here's our number line. We have the critical values of -1 and 0. So now what we're going to do is we're going to take a number from each region, plug it into the number line, or pick a number from the number line, sorry. So like -2, how about -0.5 and 1? Those work. And you're going to plug it into the first derivative. Again, let me remind you that the first derivative is 4x plus 1 over 3x to the 2/3. And you're going to take those numbers and you're going to plug it into the first derivative. So f prime of -2. So it's going to be 4 -2 plus 1 over 3 -2 to the 2/3. And you plug that in, you get -0.8399. Now that is negative. So on the number line in this region, I'm going to put a negative. Now let's try f prime of -0.5. So if we're going to plug that into the calculator, which I'm actually doing off screen, I get 1.058, which is positive, and so we have a positive in this region. Recall that positive means increasing, negative means decreasing. Now if you plug 1 in, you're just going to get, well, let's check that real fast, and 2.66 repeating, which again is positive. So we're going to put a positive here, and so that's also increasing. Okay, so let's see what we have. Do we have any local mins? Now a local min is when we're decreasing and then we're increasing. So that's actually happening right here at -1. So that's going to be local min -1, comma. Now the y value, it's a point. All right, so we need to find the y value. Now you do that by plugging it into the original function because it is a point on the graph. Recall that the original function is x to the 1/3, x plus 4. So if you plug -1 into this, you are going to get -3. Now I'll trust that you can check that. Now local max would mean that we're going up and then down. Notice that we're not increasing and then decreasing, because here this was our min, and this would be our only possible min or max, and we're going up and then up again, so nothing's happening. So we have no local max. So how about increasing and decreasing? Well, we are increasing from -1 to -1 to 0, and then again from 0 to infinity. Now could we just do -1 to infinity? We can, as long as 0 is allowed to be in the function, in the domain. Now if you go back to the original function right here, I'm allowed to plug in 0. So that means I don't have to break it up into 2. I can use that. Now decreasing, negative infinity to negative 1. Alright, so the first derivative test is done. Let's move on to concavity.